Let us start the second unit of our syllabus. So the first concept is parameterized curve in Rn. Okay, I will write the definition first. A parameterized curve in Rn is a continuously differentiable function. Okay, it is continuously differentiable function alpha defines from closed interval AB to Rn. So this is called as a parameterized curve. Okay, so I will show you here in diagram. So AB, this is one interval. Okay, we have subset of R, and alpha is a function from AB. Okay, to subset of Rn. So alpha is continuously differentiable. Continuously differentiable means alpha should be differentiable and its derivative should be continuous. Then we can say it is a parameterized curve. I would like to give you one real life example. Okay, so see, consider yes, suppose here is Ratnagiri. Okay, Ratnagiri, and here is Lanza. We want to go from Lanza to Ratnagiri. Okay, so there is a road. There is a road from Lanza to Ratnagiri. Okay, do you know how much time is required to complete this distance? 1 hour. Okay, so 1 hour, so 0 to 1. Okay, so this is a interval of R. Okay, we are starting at Lanza where when the time 0. So see, at time 0 we are at Lanza. Okay, after covering 30 minutes, that means after 30 minutes we will be at exactly middle of this curve. So after half an hour we will reach up to Pali, and at the end of 1 hour we will be at the destination, that is Ratnagiri. Getting? So it's a function from closed interval 0 1 to a subset of R3 from Lanza to Ratnagiri. So this is a parameterized curve with the help of this alpha. Okay, in terms of time we are defining the position, so that is called a parameterized curve. So now let us discuss few mathematical examples. Okay, you can make a screenshot of it, then we will go further. Okay, so let us discuss one example. Let U and V be subset of Rn. So suppose this is subset of Rn. So the U and V be elements of Rn. No, sorry, U and V be elements of Rn. Then alpha of t, we are defining alpha. Okay, we are defining alpha from where to where? 0 1 to R defined as, see, we are defining in this way: alpha of t is equal to 1 minus tu plus tv. So you know that this is equation of straight line, that means we represent line in this way. Okay, so this is a line segment joins u and v. So that means we get a line segment actually. Okay, so we are defining from close interval 0 1 to Rn. Okay, we are defining in this way. Okay, alpha of 0, what will you get? If in this definition, if you put t is equal to 0, what will you have? 1 minus 0 u plus 0 into v, which is equal to 0 into v is 0, 1 minus 0, 1 into u, that means alpha of 0, that means initially we are at u. Okay, and alpha, we have a space here, so let us utilize it. Alpha of 1, so here I have to put t is equal to 1. So what will happen? 1 minus 1 u plus 1 into v. So 1 minus 1, you know, 0, 0 into u 0, and 1 into v, v. That means at t is equal to 1, we are at the end point v. Getting? So this is a parameterization, means what? It's simply a continuously differentiable function from closed interval AB to Rn. Okay. One more example we will discuss, make a screenshot of it, then we will go further. So let us discuss second example. See, alpha from closed interval 0 to pi to R2 is defined as alpha of t is equal to cos t sin t. So clearly this is continuously differentiable, so it's a parameterized curve. So let us find the parameterized curve. Here, what is x coordinate? Cos t. What is y coordinate? Sin t. So see, what I'm going to consider, then x square plus y square, that means x is cos t, correct? So cos square t plus sin square t, which is equal to 1. So you know that x square plus y square is equal to 1 is equation of circle having center 0, 0 and radius 1. So that means this is a parameterization of a unit circle. We can check also. Okay, so let us check. Consider, see what I'm going to consider, alpha of 0. I'm taking the first value of t, 0. So what will happen if I put 0 in a definition? So we will have cos 0 comma sin 0. What is value of cos 0? 1, sin 0, 0. So that means what is happening actually? So this is closed interval 0 to 2 pi and we have a subset of R2. We are at 0. We are at, what is value of t? We have put 0. So therefore, we are at here in R2 1 comma 0. At that point we are okay. Let us go further. I am taking t is equal to pi by 2. That means alpha of pi by 2. So let us find alpha of pi by 2. So here I have to put t is equal to pi by 2. So therefore, cos pi by 2 comma sin pi by 2. Cos pi by 2 is 0, sin pi by 2 is 1. That means I will show here again 0 to 2 pi. So initially we were at 0, but now we have covered some distance and we have reached up to pi by 2. So what is happening here in R2? So initially we were at 1 comma 0, but now we have reached to 0 comma 1, getting? So 0 comma 1, that means we have traveled this much distance. So initially when we are at 0, here also we are at 1 comma 0, but if you travel a distance 0 to pi by 2, then in R2 we are covering some part of circle. Let us go further. After that, what will I do? I am going to consider alpha of pi. I am going to find alpha of pi. What will happen if I put pi here? Cos pi sin pi. You know the value of cos pi, it is minus 1, sin pi is 0. So if I draw a diagram like this, we will have this one 0 to 2 pi. Okay, so we covered now 0 to pi. Okay, this much distance. So what is happening here in R2? Initially we were at 1 comma 0, right? After that we have reached up to 0 comma 1, and what is the point we have right now? It is minus 1 comma 0. That means we have covered half of part of circle. Getting? What is the interval we have? 0 to 2 pi. Getting? Here we have covered half distance. So there also, okay, in an image set, what we are getting, we have covered a half part of circle. We can go further, but there is no more space to write. So make a screenshot of it, then we will go further. Let us consider t is equal to 3 pi by 2 now. So now alpha 3 pi by 2. Simply we have to follow the same definition. It is cos 3 pi by 2 and sin 3 pi by 2. Cos 3 pi by 2 is 0, sin 3 pi by 2 is minus 1. That means what is happening? 0 to 2 pi. Okay, so here is pi. So now we have covered a distance 3 pi by 2. Okay. So here initially we started at 1 comma 0. We have covered some part of a circle, getting, and we have reached to this point 0 comma minus 1. So this is 0 comma minus 1. That means we have covered 75% part of a circle. So let us go to the end point. Let us see what will happen. So now, what is the end point? What is the last point? The last point is 2 pi, getting 2 pi. So again I will put in definition, cos 2 pi sin 2 pi. Cos 2 pi is 1 and sin 2 pi is 0. That means 0 to 2 pi. Right now we have covered a complete interval 0 to 2 pi. So see what is happening here. We started at 1 comma 0. You remember now, we started at 1 comma 0. And what is our end point? End point is again 1 comma 0. That means here we have completed a complete round of circle. Getting? So that's why we can say this is a circle is an image of this parameterized curve alpha defined from closed interval 0 to 2 pi to R2. I hope all of you understood this example. Make a screenshot of it, then we will stop. Thank you. Bye bye.